everyone, thanks for joining us here today. My name is Dan Flynn, a member of Apple's consulting engineering team. I'm really excited to be here for virtual JNUC 2021. And joining me is my colleague, Pepijn Bruin. Pepijn?
Yeah, thanks, Dan. Hey, everybody. Super happy to be here for virtual JNUC 2021. Today we're going to talk about keeping private data private. Dan, take it away.
Keeping private data private, or basically how Apple platforms protect the confidentiality and integrity of this private data. The 2021 Worldwide Developers Conference announced exciting updates to iOS, iPadOS, macOS, and watchOS. For enterprise and education, many of these announcements will have a big impact on what's to come over the next year. Deployment and security enhancements for Mac, new management capabilities to control the flow of corporate data on iPhone and iPad, new BYOD capabilities, and laying the foundation for a new management protocol designed for performance and scalability. Here are just some of the highlights of what's new for device management, which we will cover in detail later on. For IT teams, it's not just about the new device management features, it's also how they impact security. Apple platforms have a long list of security features to protect data from compromise. Security is a process, not a destination, and Apple continually improves platform security in the face of emerging threats. For our session today, we are going to focus on data separation. From the very core of the design, Apple platforms are specifically designed to protect data from unauthorized access. This includes attackers with physical access to the device, attackers in privileged network positions, and attackers attempting to get remote code execution on the device. The defense in depth approach in Apple platform security protects data at every level, from process and memory to file system and networking layers. This helps ensure that only authorized users and processes have access to the intended data. Policy controls can also be applied to mitigate the likelihood of accidental disclosure of data by authorized users. Apple platforms are designed to seamlessly separate work and personal data without frustrating the user or degrading their experience, which is critical for supporting productivity. It's important for security mechanisms to be as transparent as possible. If a user has to make a decision on the security implications of working with a piece of data, they might make a mistake, potentially putting the confidentiality or integrity of the data at risk. If the security measures in place create an unnecessarily large burden on the productivity workflows, users might discover workarounds that bypass these measures, putting the data at risk. Apple platforms seek to provide the appropriate balance of productivity and security, with built-in secure design and flexible management policies that can be tailored to the classification of the data in question. Today, we're going to briefly review industry standard best practices in security models and secure design, and describe how Apple platform security design principles align with these practices, as well as list some additional policy controls that can be implemented to further reduce attack surface to achieve the appropriate balance between productivity and security requirements based on the data's classification. When designing a security practice, it's important to classify the data that is necessary to protect. I'd like to take just a few minutes to review some industry best practices on data and asset classifications and the security models that govern the flows of information. In order to protect data appropriately, it is critical to identify the impact if that particular piece of data has its confidentiality, integrity, or availability violated. The higher the impact, the higher the classification. Data of a particular classification should only be able to be modified directly by device assets specifically designed for that classification. The classification labels you see here on the left are what might typically be seen in the commercial sector, with common government counterparts on the right. The data classification level is determined by the damage incurred if there is a violation of the data's confidentiality, integrity, or availability. A compromise of data that would have severe or catastrophic impact on organizational operation, making it unable to perform its primary functions, or in the case of government agencies, national security implications, this would be the highest classification, in this case confidential, top secret. A data compromise that would have serious impact, significantly reducing the ability to perform primary functions, but still allow for some organizational operation, might be given the private or secret classification label. Where compromise of a particular class of data would only result in a noticeable but not quite severe reduction in organizational functionality, this might be given the sensitive or confidential label. Everything else would be classified as public or unclassified, where compromise of this data would have no discernible impact on organizational objectives. Security models are the rules that define under what circumstances data is allowed to be modified or moved between classifications. Some models emphasize protection of confidentiality. Others prioritize integrity. For example, if confidentiality is the priority, assets of a particular classification cannot be used to read data of a higher classification, nor can they write data to a lower classification. For example, a device designed for sensitive data cannot directly read data in the private or confidential classes. Similarly, a device protecting confidential data cannot copy that data to a device designed for private or lower classifications. If integrity of the data is the priority, assets of a class may not read data at a lower class and cannot modify data at a higher class. A model like this might be used where it's important to ensure data isn't tampered with than it is ensuring that it's kept private. For example, in a public ledger system, it's more critical to ensure the integrity of the transaction than it is to preserve its confidentiality. The model used by an organization is determined by the specific needs of the business, and in reality often includes properties of both protecting confidentiality and preserving integrity. These security models rely on a trusted computing base. The integrity of the computing base or platform must be reasonably assured from which to build a secure foundation. Here is an overly simplified description of how these models might interact. For example, in an online banking situation. A financial services institution considers their customers' account data at a high classification, at least private or confidential. Yet a customer may be able to access some of their data through online banking through a web browser or app on a device beyond the bank's control. The user on a public asset, or at least from the bank's perspective, can interact with confidential data on an asset designed to protect confidential data. However, the user cannot read or modify the data directly. Only the database server that protects the data has the authorization to do that. To interact with the data, the user must perform some sort of authentication to an intermediary web server. Upon success, the user performs a request, and the web server determines whether the user is authorized for such an action. For example, reading their own account balance is authorized, but reading that of another user or a different row in the database table is not. The web server performs queries on the database using a service account or cryptographic keys to return only the data authorized for the authenticated user. All transactions are diligently logged for accountability purposes. But note that at no point is the user on the public asset reading or modifying the confidential database directly. Instead, the data is presented through a constrained web view via a separate web front end to separate the duties and privileges. Additionally, access controls are in place to verify the authenticity and integrity of the transactions to prevent fraud. Each key in this graphic refers to this process: authentication, authorization, and accounting of the transactions. Security models govern the rules by which data of specific classifications can be accessed. In the online banking example, while the public computer asset is interacting with the private data, it is only doing so indirectly and through strict authentication, authorization, and accounting rules. The database is never copied or accessed directly by either the user's computer or the intermediary web server. For all this to function properly, it is critical to ensure the integrity of the computing base for these security models to be effective. Secure design principles are used to provide data separation at an architectural level. Secure design begins with a trusted computing base that verifies its integrity and is secure at every boot. The principle of least privilege limits access to data and resources to the minimal amount required for completion of the specific task. Enforcing bounds puts limits on memory addresses and resources based on the authority level. A process that is confined by bounds is isolated, and other applications and the operating system are protected in case the process is compromised or abused. Let's look at how Apple platform security features implement security architecture best practices. Pepijn?
Thanks, Dan. So, one way Apple platform security ensures the integrity of the system is with Secure Boot. Secure Boot begins in hardware and builds a chain of trust through software, where each step is designed to ensure that the next is functioning properly before handing over control. Replacing kernel extension functionality with user space alternative is just one example of the privilege of least privilege. Processes are limited with boundaries around what data they are authorized to modify directly and are isolated from one another in case of compromise or abuse. Apple Platform Security is designed from the silicon up to ensure the integrity of a trusted computing base. With Secure Boot, each step of the startup process contains components that are cryptographically signed by Apple to enable integrity checking so that boot proceeds only after verifying the chain of trust. These components include the bootloaders, the kernel extensions, and cellular baseband firmware. This secure boot chain is designed to verify that the lowest level of software are not tampered with. The signed system volume features a kernel mechanism that verifies the integrity of the system content at runtime and rejects any data, code and non-code, without a valid cryptographic signature from Apple. SSV not only helps prevent tampering with any Apple software that's part of the operating system, it also makes macOS software update more reliable and much safer. System integrity protection, meanwhile, restricts components to read-only in specific critical file system locations to help prevent malicious code from modifying them. macOS applies this security policy to every process running on the system, regardless of whether it's running sandboxed or with administrative privileges. iOS and iPadOS don't allow users to install potentially malicious unsigned apps from websites or to run untrusted apps. At runtime, code signature checks that all executable memory pages are made as they are loaded to help ensure that an app hasn't been modified since it was installed or last updated. App security in macOS consists of a number of overlapping layers, the first of which is the option to run only signed and trusted apps from the App Store. In addition, macOS layers protections help ensure that apps downloaded from the internet are free of known malware. macOS also offers technologies to detect and remove malware, including additional protections designed to prevent untrusted apps from accessing user data. Services from Apple such as Notarization, XProtect, and updates for the malware removal tool are designed to prevent malware installation and, when necessary, to provide for a quick and efficient detect and respond process to block and remove any malware that may have at first avoided detection. Apple platforms include many layers of defense to protect the system from the earliest stages of the boot process up to and including execution of user space processes. Apple platforms employ the principle of least privilege to reduce attack surface and to limit damage resulting from a compromised or malicious application. macOS enables developers to extend the capabilities of macOS by installing and managing system extensions that run in user space rather than at the kernel level. By running in user space, system extensions increase the stability and security of macOS. Even though KEXTs inherently have full access to the entire operating system, extensions running in user space are granted only the privileges necessary to perform their specified function. Access by third-party apps to user information and to features such as iCloud and extensibility is controlled using declared entitlements. Entitlements are key value pairs that are signed into an app and allow authentication beyond runtime factors, like Unix user ID. Since entitlements are digitally signed, they can't be changed. Entitlements are used extensively by system apps and daemons to perform specific privileged operations that would otherwise require the process to run as root. This greatly reduces the potential for privilege escalation by a compromised system app or daemon. So we've talked about system extensions for a number of years now. Introduced in macOS Catalina, they are APIs to allow developers of apps for endpoint security, networking, file providers, and printers and scanners to build apps that are outside of the system kernel. Vendors who use kernel extensions, or KEXTs, should instead use these new system extensions to provide existing and new functionality while keeping the system kernel secure. As IT administrators, we know you use device drivers, file providers, networking, and security apps that may still require kernel extensions. We encourage you to talk with your vendors about getting them to move to newer versions that are built on system extensions as soon as possible. In some cases, that may mean you need to switch vendors. By adopting system extensions, vendors can greatly reduce the possibility of kernel panics on Mac computers because they run in user space, reduce the attack surface, and are manageable using MDM. In macOS 11.3, installing the system extension payload changes the state of a system extension. For example, if a system extension is pending user approval, installing the payload will activate the extension. Conversely, removing the payload will deactivate the system extension. After a system extension is deactivated, it will be marked for removal on the next reboot of the Mac. This allows for an automated removal capability for IT by revoking the system extension's approval applied via MDM, and then restarting the device. To make it even easier to remove a system extension in macOS Monterey, there's a new configuration option called Removable System Extensions, which can be set in the configuration profile used to configure system extension approvals. An app in this list can deactivate its own system extensions, for example, when the app installs itself. With this key set, there will be no admin password required to remove the system extension, allowing it to be completed in a fully automated way. Apple platforms enforce boundaries around what applications and processes can and cannot do to prevent abuse and to limit damage. All third-party iOS apps are sandboxed, so they are restricted from accessing files stored by other apps or from making changes to the device. Sandboxing is designed to prevent apps from gathering or modifying information stored by other apps. Each app has a unique home directory for its files, which is randomly assigned when the app is installed. All Mac App Store apps, and even many distributed outside the Mac App Store, are also sandboxed, and use a technology called PowerBox to read and write files. PowerBox provides a file reference to the Mac app so that it's not necessary for the app to have users' POSIX file systems permissions. Apps and extensions owned by a given developer account can share content when configured to be part of an app group. It's up to the developer to create the appropriate groups on the Apple Developer Portal and include the desired set of apps and extensions. App groups restrict access to shared containers, preferences, and keychain secrets to only the developer that created them. Apple uses operating system kernels to enforce protection and security. The kernel uses access controls to sandbox apps, which restrict what data an app can access, and a mechanism called a data vault, which rather than restricting the calls an app can make, restricts access to the data of an app from all other requesting apps. Apple devices help prevent apps from accessing a user's personal information without permission using various technologies, including Data Vault. In settings in iOS and iPadOS or system preferences in macOS, users can see which apps they have permitted to access certain information as well as grant or revoke any future access. In iOS 13.4 or later and iPadOS 13.4 or later, all third-party apps automatically have their data protected in the Data Vault. Data Vault helps protect against unauthorized access to the data, even from processes that aren't themselves sandboxed. Apple believes that users should have full transparency, consent, and control over what apps are doing with their data. In macOS 10.15, this model is enforced by the system to help ensure that all apps must obtain user consent before accessing files in Documents, Downloads, Desktop, iCloud Drive, and network volumes. In macOS 10.13 or later, apps that require access to the full storage device must be explicitly added in system preferences. In addition, accessibility and automation capabilities require user permission to help ensure they don't circumvent other protections. Apple platforms also isolate processes from one another. Address Space Layout Randomization, or ASLR, helps protect against the exploitation of memory corruption bugs. Built-in apps use ASLR to help randomize all memory regions upon launch. Randomly arranging the memory addresses of executable code, system libraries, and related programming constructs reduces the likelihood of many exploits. Execute Never marks memory regions non-executable. The kernel checks for the presence of the Apple-only dynamic code signing entitlement. Even then, only a single mmap call can be made to request an executable and writable page, which is giving a randomized address. Safari uses this functionality for its JavaScript just-in-time compiler. XPC, meanwhile, allows developers to create lightweight helper tools that perform work on behalf of an application. Segmenting the duties of an application using XPC services creates privilege separation in the event an application crashes or is compromised. Apple platforms protect data at rest from unauthorized access. The secure boot chain, system security, and app security capabilities all help to verify that only trusted code and apps run on a device. Apple devices have additional encryption features to safeguard user data even when other parts of the security infrastructure have been compromised. For example, if a device is lost or is running untrusted code. All of these features benefit both users and IT administrators, protecting personal and corporate information and providing methods for instant and complete remote wipe in the case of device theft or loss. iOS and iPadOS devices use a file encryption methodology called data protection, whereas the data on an Intel-based Mac is protected with a volume encryption technology called FileVault. A Mac with Apple Silicon uses a hybrid model that supports data protection with two caveats. The lowest protection level, Class D, isn't supported, and the default level, Class C, uses a volume key and acts just like the FileVault on an Intel-based Mac. In all cases, key management hierarchies are rooted in the dedicated silicon of the secure enclave, and a dedicated AES engine supports line speed encryption and helps ensure that long-lived encryption keys aren't exposed to the kernel or operating system or CPU, where they might be compromised. The Secure Enclave coprocessor in iOS, iPadOS, and macOS enforces rate limits to mitigate brute force attacks on the passcode. Apple platforms protect data in transit from attackers in privileged network positions. App Transport Security provides default connection requirements so that apps adhere to best practices for secure connections when using NSURL connection, CFURL, or NSURL session APIs. By default, App Transport Security limits cipher selection to include only suites that provide forward secrecy. Evaluating the trusted status of a TLS certificate is performed in accordance with established industry standards and incorporates emerging standards such as certificate transparency. In iOS 11 or later and macOS 10.13 or later, Apple devices are periodically updated with a current list of revoked and constrained certificates. The list is aggregated from certificate revocation lists, or CRLs, which are published by each of the built-in root certificate authorities trusted by Apple, as well as by their subordinate CA issuers. The list may also include other constraints at Apple's discretion. This information is consulted whenever a network API function is used to make a secure connection. If there are too many revoked certificates from a CA to list individually, a trust evaluation may instead require that an online certificate status response, or OCSP, is needed. And if the response isn't available, the trust evaluation will fail. iOS, iPadOS, and macOS support the following: VPN on demand for networks that use certificate-based authentication. IT policies specify which domains require a VPN connection by using a VPN configuration profile. Per app VPN, this is for facilitating VPN connections on a much more granular basis. Mobile Device Management, or MDM solutions, can specify a connection for each managed app and specific domains in Safari. This helps ensure that secure data always goes to and from the corporate network, and that a user's personal data doesn't. iOS and iPadOS, meanwhile, also support always-on VPN. This can be configured for devices managed through an MDM solution and supervised using Apple Configurator 2, Apple School Manager, or Apple Business Manager. Always-on VPN eliminates the need for users to turn on VPN to enable protection when connecting to cellular and Wi-Fi networks. Always-on VPN gives an organization full control over device traffic by tunneling all IP traffic back to the organization. The default exchange of parameters and keys for the subsequent encryption, IKV2, secures traffic transmission with data encryption. The organization can monitor and filter traffic to and from its devices, secure data within its network, and restrict device access to the internet. And now, back to Dan.
Thanks, Pepijn. Everything you've seen so far you get for free as it is built into Apple platforms. For additional attack surface reduction, policies can be enforced with MDM to protect data of higher classifications from unauthorized access by more sophisticated threat actors or from accidental disclosure by an authorized individual. A loss of confidentiality, integrity, or availability of confidential data could result in the inability of an organization to perform its primary functions. An example might be the private signing keys of a certificate authority. Compromise of those keys would likely result in the CA ceasing to exist. Therefore, it would be critical to protect signing keys using every available means. The high cost of compromise justifies a high cost of countermeasures to protect this critical data. Assets that protect data of lower classifications should be protected with countermeasures commensurate with the value of the loss expectancy. Some security safeguards have negative productivity trade-offs, so it's important to quantify this impact when calculating the total cost of protecting an asset from a risk. There is no financial benefit if the cost of the safeguards exceeds the cost of the realized risk. Therefore, it is critical to balance the countermeasures with the classification of the asset protecting the data. Management policies can be applied to Apple platforms to reduce the attack surface to a level that is appropriate for the classification of data that the device is authorized to manipulate. If the asset is working on data at a high classification, where the loss of confidentiality or integrity could result in a catastrophic impact to the organization's ability to meet its goals, then it will likely be desired to have the strictest controls over the information flow. These controls are available through supervision and automated device enrollment. However, for BYOD assets that work with data at the lowest classifications, where the loss of confidentiality or integrity would only result in a negligible impact to the organization, user enrollment provides flexibility and transparent separation of data. When users bring their personal devices to work, they don't want IT managing the entire device. And IT teams really don't want to fully manage personal devices. The whole idea is to strike a better balance between security and configurations that IT needs and the privacy concerns that a user might have with an IT department managing their device. User enrollment is a great device management option that balances user privacy and data separation in BYOD deployments. Its design allows the user to be comfortable that their privacy and personal data are protected, while the organization can be confident their data is secure. User enrollment requires managed Apple IDs for users. Managed Apple IDs are owned and managed by the organization and provide access to Apple services such as iCloud. They are used alongside a personal Apple ID for user enrollment. Managed Apple IDs are created within Apple Business Manager or Apple School Manager. They can either be created manually or can be automated through federation with Azure Active Directory. Additionally, schools can connect to a student information system to automate creating managed Apple IDs. The second component of user enrollment is data separation, which means, quite literally, we are separating the data on the device. User enrollment creates a separate APFS volume for managed accounts, apps, and data on the iPhone and iPad. This managed volume is cryptographically separate from the rest of the device. When the device is unenrolled from the MDM solution, the keys and the separate volume are both destroyed and any organization-owned apps are removed. Finally, management capabilities are curated specifically for BYOD, so IT can configure settings like passcode policy or deploy apps, but cannot access personal information or remotely wipe the device. Managed apps and data is supported in user enrollment too. Managed open-in allows you to control whether data is allowed to enter or leave the management sphere. At its most basic, it controls independently whether data can be sent from an unmanaged app to a managed app, and vice versa. MDM solutions provide specific features that enable corporate data to be managed at a granular level so it does not leak out to users' personal apps and cloud services. Managed open-in uses a set of restrictions that prevent attachments or documents from managed sources from being opened in unmanaged destinations, and vice versa. For example, you can prevent an email attachment in your organization's managed mail account from being opened in any user's personal apps. Only apps installed and managed by MDM can open this document. The user's unmanaged personal apps do not appear in the list of apps available to open the attachment. In addition to managed apps, accounts, books, and domains, several extensions respect managed open-in restrictions as well. Conversely, if the user has a personal document from a personal account, this restriction prevents the personal document from opening in the user's apps that are being managed by MDM. Most important, managed open-in allows IT to seamlessly separate work and personal data without frustrating the user. And now we're making it better than ever with managed Pasteboard. IT teams will have new controls to choose whether copy or paste is allowed between managed and unmanaged apps. This is a powerful new tool to help prevent corporate data from ending up in the wrong place. This is how user enrollment balances user privacy with the need to secure organizational data. Personal devices can be configured with a corporate account, VPN settings, and require a 6-digit passcode. But IT cannot access personal information or remove personal accounts. IT can also deploy organization-owned apps, but they cannot take over personal apps or remotely wipe the entire device. In iOS and iPadOS 15, there are new updates to user enrollment that will make it better than ever to support personal devices. First, a new streamlined user enrollment process has been built right into the Settings app to make it easier for users to enroll their personal devices. To begin, the user navigates to the redesigned VPN and device management section in Settings and taps the new Sign in to Work or School button. As they enter their managed Apple ID, Service Discovery will identify the MDM solution's enrollment URL. The user enters their organization's username and password. Once the organization's authentication succeeds, the enrollment profile is sent to the device. Additionally, a session token is issued to the device to allow for ongoing authentication. Finally, once a user is signed in, the new managed account is displayed prominently within the Settings app. Users can see details about what is being managed on their personal device and how much iCloud storage space is provided by their organization. New in iOS 15 and macOS Monterey, managed Apple IDs support iCloud Drive. iCloud Drive is an important feature of iCloud accounts, and now it will be available to user-enrolled devices. On iOS and iPadOS, it shows up as a new location in the Files app. Document browser-based apps will also have access to the additional iCloud Drive. And on macOS, it appears as an additional location in Finder. And of course, iCloud Drive will respect managed open-in restrictions for managed apps and data access. With iCloud Drive for managed Apple IDs, organizations are now able to easily provide their users a built-in cloud storage solution. In macOS Big Sur, we enabled managed apps on macOS for the first time. This allows organizations to install apps on a managed device, similar to how they can for iOS, including support for managed app configuration and feedback. It also provides the ability to remove the app with an MDM command or when a device unenrolls from MDM. New in macOS Monterey, for user enrollments into MDM for BYOD environments, just like on iOS, managed app data is separated on a different volume. When the app is removed, the data container is also erased. Managed apps that use CloudKit will now use the managed Apple ID associated with the MDM profile. Your MDM vendor should install apps as managed to take advantage of this functionality. User enrollment is an ideal choice for BYO deployments that balances user privacy with institutional data separation. However, if the device is manipulating data of a higher classification and requires additional safeguards to protect this data from greater threats, automated device enrollment and supervision provide more management capabilities to reduce the attack surface accordingly. Automated device enrollment is for institutionally owned and operated devices, supports the broadest range of policies, and is flexible enough to protect data of a wide variety of data classifications. Papine?
Thanks, Dan. Automated device enrollment is the best way for IT to deploy organization-owned Apple devices directly to users. It provides a fast, streamlined way to deploy all your organization-owned devices. It automatically enrolls organization-owned devices into your MDM solution so you don't have to physically touch devices to provision them before users get them. Automated device enrollment enables supervision and can be customized based on your organization's needs. Supervision provides a higher level of management for corporate-owned devices, allowing for additional restrictions and configurations. With previous releases, Apple introduced support for enrollment customization to enhance the provisioning process by allowing IT to provide custom branding, consent text, and multi-factor authentication to users via WebSheet. This provides an even better experience while also allowing IT to protect the setup process using their existing authentication services, like Azure AD, Okta, Ping, or others. Additional settings include skipping specific setup assistance screens, including screens shown after a software update. Once devices are enrolled into MDM, IT admins have a wide range of tools to manage iPhone, iPad, Mac, and Apple TV. Configuration profiles consist of payloads that load settings and authorization information onto Apple devices. They automate the configuration of settings, accounts, restrictions, and credentials. Restrictions can be enabled, or in some cases disabled, by administrators to help prevent users from accessing a specific app, service, or function of an iPhone or iPad. Management tasks can take specific actions on devices, like remotely wiping a device or installing a software update. An MDM can query inventory data about your managed devices, so you can keep track of them and ensure they meet your compliance standards. Here are examples of the different payloads that can be built and deployed to manage devices using an MDM solution. IT teams can enforce passcodes or deploy custom fonts. Account information can be configured so users can access their email, contacts, and calendars automatically. Network information like Wi-Fi and VPN can be set up for your users as well as the certificates required for those connections. DNS proxy, DNS over HTTPS or over TLS, Web content filters, web proxies, and VPN can all be used to prevent devices from accessing malicious network resources. Host pairing can be managed to prevent the device from pairing with unknown hosts over USB. These are just some examples of strong policy controls to consider against more advanced threats. Additional restrictions allow you to enforce your security policies and help users stay focused on their task. Features like Managed Pasteboard and Managed Open-In that we outlined earlier are all part of the restrictions payload. Other restrictions include the ability to disable iCloud Keychain, iCloud Backup, or the App Store. Restricting iCloud features can prevent data leakage or avoid data sovereignty situations. You can even hide or show any apps you want, be they third-party apps or system apps, with the exception of the phone and settings apps. This can be used so that the device only runs approved software. A device enrolled in MDM can also be administered through a number of direct management tasks, giving you powerful remote capabilities. Two we should highlight here are Lost Mode and Clear Activation Lock. Lost Mode was designed to be the ideal situation for locating misplaced devices. It allows MDM to collect location information for a device it has placed in Lost Mode. Lost Mode strikes a balance between user privacy and IT control by locking the device with a customized message and contact information for the organization, so that anyone who finds the device is aware that it is being tracked. Most importantly, Lost Mode does not require the user to grant access to location services. And actually, location services can be turned off and Lost Mode will still work. Lost Mode is supported for iPhone and iPad. Theft deterrence is made easier for Apple School Manager or Apple Business Manager managed devices by using device-based activation lock. By leveraging device-based activation lock, MDM gets to enable or disable activation lock directly with Apple servers without the need to interact with the device or the user's iCloud account. If using user-based activation lock, MDM can still gather a bypass code and use it to clear activation lock with a command sent to the device. New in macOS 11.5 as well as macOS Monterey, we are enhancing the device lock command on Mac computers with Apple Silicon. With this change, you can now send a 6-digit PIN, message, and phone number to lock the device. This will cause the Mac to reboot and present the user with the information provided, bringing feature parity across all Mac models. This can be used to prevent a rogue insider or attacker with physical access to the device from accessing or modifying data on a Mac with Apple Silicon, while still preserving the data for forensic analysis. With remote lock in place, the user is unable to use the Mac until the PIN has been provided. Once the PIN is entered, the Mac will reboot with all data intact and ready for login. Note that if you send this command to a Mac with Apple Silicon running a version of macOS prior to 11.5, it will be deactivated and require reactivation by a secure token-enabled administrator account. If you deploy in a way that results in no secure token-enabled administrators being created by default, you should avoid sending the device lock command to those Mac computers with Apple Silicon until they are running macOS 11.5 or later. We're also adding a new feature to set a recovery password. The recovery password for Apple Silicon is new in macOS 11.5 and macOS Monterey and prevents users from accessing the recovery environment, including both RecoveryOS and the startup options screen. This is an effective control to deter malicious users from wiping the system, as well as preventing administrator users from downgrading the boot security of the device. It can only be set and removed by MDM. If a device is unenrolled from MDM by either the user or the server, the recovery password will be removed. To set a new password, you need to know the existing password and provide it in the MDM command along with the new one. Note that both the device lock PIN and the RecoveryOS password can be removed if a Mac is erased using DFU mode. So we recommend using these features in conjunction with managing and allowing activation lock whenever possible to provide the best security for your Mac fleet. And this is what the RecoveryOS password screen looks like. Very similar. Meanwhile, MDM can query information that can help assess the state of your deployment. You can get the name of your devices, which can also be remotely set and locked. Battery level data can help to get a sense of your user's ability to get all-day battery life. And roaming status can help alert you to potential costly cellular charges. Also on macOS, MDM can query for system integrity protection and boot security status. MDM queries return the state of a device for a wide variety of configurations. Open source and commercially available client management and agents can provide for additional telemetry on the behaviors on macOS. Please see Apple Security Certifications and Compliance Center for third-party certifications and attestations for Apple operating systems, hardware, software, and services. The Security Certifications and Compliance Center can be found at support.apple.com/guide/SCCC. Another resource that can help with auditing is the macOS Security Compliance Project. This project is an open source effort to provide a programmatic approach to generating security compliance based on certain baselines. The macOS Security Compliance Project can be used as a resource to easily create customized security baselines of technical security controls by leveraging a library of atomic actions which are mapped to the compliance requirements defined in NIST 800-53 Revision 4. It can also be used to develop customized guidance to meet the particular cybersecurity needs of any organization. Apple Professional Services is working on several offerings to assist companies with macOS security compliance. For further information, contact your Apple Systems Engineer or Professional Services representative. So, to review, good security modeling limits data to assets with the same classification. Secure design principles put proper boundaries on the system to keep processes and data appropriately separate. Platform security in Apple products protects data from unauthorized access, is built into the operating system, and is enabled by default. Additional policies can be applied to reduce attack surface even further to bring the device into compliance with the required asset classification appropriate for the class of data it is protecting. These policies can then be categorized for the classification, balancing the threat model and business use case. And now, back to Dan to take a look at the various resources that Apple has available to help support you with deployment.
Great, thanks, Pepine. All Apple security documentation is available on the Apple Platform Security website. This documentation now lists all software, hardware, and services features across platforms and includes new information around macOS security that was not previously published. If you're interested in testing new Apple software, any non-student managed Apple ID from Apple School Manager or Apple Business Manager can participate in our AppleSeed for IT program. This program allows you to get access to pre-release Apple software for testing in your environment. It includes detailed test plans and puts your feedback into a dedicated queue where issues and enhancements are reviewed by a team focused on enterprise and education institutions. The release notes are also targeted at education and enterprise, which allows us to highlight any impactful changes or issues in the operating systems for these organizations. Last year, we added the ability to more easily track feedback filed by everyone within your organization by introducing teams. You can easily reassign feedback to other colleagues to be able to more quickly provide responses to Apple when additional information is requested. We also made it easier to capture diagnostic information from multiple devices, as long as they're logged in to the same iCloud account, using a feature called multi-device diagnostics. This is especially helpful when filing feedback on services that often require logs from multiple devices, such as with continuity or AirDrop. So thank you so much for joining us here today, and we hope you enjoy the rest of this virtual JNUC 2021.